we are given this circuit for problem 1. This circuit consists of a power supply X of t, and our circuit is also composed of two resistors R1 and R2. It is also composed of one capacitor and one inductor, and our goal is to relate the input X of t, which is a voltage input, to its output voltage Y of t. So the goal is to obtain a differential equation which relates both. And an important equation to keep in mind while solving this problem is that the current through the capacitor is equal to its capacitance multiplied by the derivative of its voltage. So we're first going to start off by applying KCL at this node, and we are going to define the current through the capacitor as I1, the current through R1 as I2, and the current through R2 as I3. So we are going to use KCL to obtain our final answer. So we're going to define it as I1 plus I2 plus I3 is equal to 0. And we could then replace I1 by the current through the capacitor, which is C dV of t dt. And then we could replace I2 using 1 over R1 V of t minus X of t plus 1 over R2 multiplied by V of t minus Y of t, and you would equate all of this to 0. And now we could multiply the whole equation by R1, and we would obtain R1 C dV of t dt plus V of t minus X of t plus R1 over R2 multiplied by V of t minus R1 divided by R2 multiplied by Y of t, and all of this equal to 0. So this is our first, we're going to further simplify this equation, and we are going to obtain R1 multiplied by the capacitance times the derivative of V plus in brackets 1 plus R1 divided by R2 multiplied by V of t minus R1 divided by R2 multiplied by Y of t, and all of this is going to equate to X of t, which is brought to the other side of the equal sign. So this is our first important equation, which is going to be used in solving our circuit equations to obtain our ODE in terms of Y of t and X of t. So now we're going to apply KCL at this corner in order to obtain a second equation, which will then be used to replace our V of t function, which we want to get rid of. So once again, we are going to use KCL as our method of solving. So our equation is going to be Y of t minus V of t divided by R2 plus 1 over L, and we're going to take the indefinite integral of Y of t dt. So we are going to obtain the current through the inductor by this equation, and then following this we can separate this equation into Y of t divided by R2 minus V of t divided by R2 plus our indefinite integral. And all of this equates to 0 once again. And then if we further derive this equation and then simplify it, we want to do so because we want to get rid of the integral. So we would obtain dy of t dt plus R2 divided by L multiplied by Y of t. And all of this would be equal to dV of t. So now we have reached our second important equation in solving the ODE. And we are going to use this second equation to replace the V of t in the other equation. But in order to do so, we are going to have to take the second derivative of the first equation. And then after that, we are going to be able to replace the dV dt term in the first equation, which would leave us with simply a Y of t terms as well as a X of t terms in the equation, which is the solution we're looking for. So we would obtain R1 times C second derivative of V of t plus in brackets 1 plus r1 divided by r2 multiplied by the first derivative of v of t minus r1 over r2 multiplied by the first derivative of y of t, and all of this would be equal to the derivative of x of t. So then if we apply substitution, replace our dv dt from the equation above into the equation we just wrote down, we would obtain a function that is composed only of y of t's and x of t's. So we would obtain R1 multiplied by the capacitance, and in brackets we would obtain second derivative of y of t multiplied by second derivative of y plus R2 divided by L multiplied by the first derivative of y plus in brackets 1 plus R1 divided by R2 multiplied by the first derivative of y plus R2 divided by L, and this multiplied by y of t. And if we keep on going, we would then get minus R1 divided by R2 multiplied by the first derivative of y of t, and this would be equal to the first derivative of x of t. And then all we have to do now is simplify our equation and group our common terms, and we would obtain r1 multiplied by c, second derivative of y of t, plus in brackets r2 divided by L plus 1 multiplied by our first derivative of y of t plus in brackets 1 plus r1 divided by r2 multiplied by y of t, and all of this would be equal to our first derivative of x of t. So this is our final solution to the circuit. We have found an ODE which relates its input to its output. Part 2 of this video problem, we are given this signal x of t, which is given in its trigonometric Fourier series form. So this signal is equal to 3 plus square root of 3 multiplied by cosine 2t plus sine 2t plus sine 3t minus a half cos 5t plus pi over 3. The first part is going to consist of rearranging this equation using trigonometric formulas to obtain a signal in which it is easier to graph its spectra. So what we can do is, looking at these two terms right here, they have the same frequency, so we could rearrange them to obtain one cosine function to minimize the number of terms in our signal. So for example, constant A, which is going to be the magnitude, is going to consist of square root of 3 squared plus 1 squared, and all of this is going to be equal to 2, and our angle theta is going to be equal to arctan of -1 divided by root 3, and this is equal to negative pi over 6. So the next thing we could do is convert this sine 3t right here into a cosine. So sine, this is going to be our first step, this is going to be our second step. Sine 3t could be rewritten as cos of 3t. So we have the same frequency, but we have a shift of pi over 2. And our third step is making sure to simplify the last term right here. We want to get rid of the negative in front. So what we're going to do is that negative half cos 5t plus pi over 3, we could rewrite this equation as a half cos 5t, and inside the brackets of the cosine function, we are going to minus by a value of pi. So then our final resulting angle is going to be of minus 2 pi over 3. So if using all these three steps, we could rewrite the signal such that x of t is equal to 3 plus 2 cosine of 2t minus pi over 6 plus cosine 3t minus pi over 2 plus a half cosine 5t minus 2 pi over 3. So this is our simplified form of our signal, and from this we could extract the Fourier spectra for x of t. So first off, we're going to start by the coefficients Cn on the y-axis and n, which is an integer multiple of the fundamental frequency. So we are going to obtain a graph like this. We have Cn on this graph, and on this side we are going to get as a function of n. The values looking at our function, that they're going to take the following values on the y-axis. There's going to be a value of a half from the last term. There's going to be a value of 1 for the before last term, a value of 2, and for our constant, a value of 3. On our x-axis for our n, we notice that for the frequencies here, here, and here, and this one has a 0n. So at 0, we obtain a Cn of 3. At n is equal to 2, we obtain a Cn of 2 as such. At 3, we obtain a Cn of 1. Let me label my x-axis. So this was at 2, 0, we have 3, and our last one is at n is equal to 5. We will obtain a Cn of a half, which is demonstrated in this graph by looking at the above signal. Now the following step is graphing the theta graph, and looking at this, we see that there is a shift in the angle for n is equal to 2, n is equal to 3, and n is equal to 5. And all these shifts in thetas are all negative, so our graph is going to look as such. We have theta n, and here we have our n axis. So as I just said, we're going to get a phase theta difference for n is equal to 2, n is equal to 3, and n is equal to 5. At n is equal to 2, we're going to get a phase difference of negative pi over 6. At n is equal to 3, we are going to obtain a phase of negative pi over 2. And at n is equal to 5, we are obtaining a phase of negative 2 pi over 3. And this is our Fourier spectrum. Now, using this information that we just graphed, we could obtain its exponential exponential Fourier spectrum for x of t. Because we know that d naught is c naught, and we know that dn is equal to the same thing as the magnitude of d when n is negative, and all of this is equal to half of Cn. And we know that the phase dn is equal to theta n, and when it's negative n, it's equal to negative theta n. So using this information, we can come up with the graph for d of n, for the magnitude of d of n. So first off, we have our y-axis like this. We get our x-axis, and we know that by the formula, it's half SCN. So looking back at the above one, we know it's the same thing, except for 0, which is equal to C naught. The rest have a magnitude half on the CN axis. So now this is our DN axis, and here we have our axis N. So at N is equal to 0, we still obtain a height of 3. At N is equal to 2, we obtain a height of 1. At N is equal to 3, we obtain a height of a half. And at N is equal to 5, we obtain a height of a quarter. But now we know that this is replicated as well on the negative N axis. So we would simply obtain the following. And this would be our graph for dn. Now looking at the phase, we would obtain something similar where there's the negative axis which is taken into account. So for dn, we would have our y-axis like such, and we have our x-axis, and our plot would look identical to our first one here. However, we would have the same reflection on the negative n axis, but it would be towards the positive theta n. So our graph would look like this, where at n is equal to 2, we would obtain a value of negative pi over 6. At 3, we would obtain a value of negative pi over 2. And at 5, we would obtain a value of negative 2 pi over 3. And on our negative axis, at negative 2, we would obtain a value of pi over 6. At negative 3, we would obtain a value of pi over 2. And at negative 5, we would obtain our final value, which would be negative 2 pi, which would be positive 2 pi over 3. And by inspecting these graphs, we can come up with the exponential form of x of t. So by doing so, we would notice that our x of t is equal to 3 plus 1 times e to the j brackets 2t minus pi over 6 plus e to the negative j 2t minus pi over 6 plus a half e to the power of j 3t minus pi over 2. All this plus e to the power of j3. This would be negative j 3t minus pi over 2. And to all this, we add 4 times e to the j multiplied by 5t minus 2 pi over 3 plus e to the negative power of j multiplied by 5t minus 2 pi over 3. And all this would be our representation in the exponential form. And we can see that this is equivalent because if we convert this back to our original signal, we would see that we would obtain 3 for the first one. Our first term would give us 2 cos 2t minus pi over 6. Our second term would give us plus cos 3, oops, sorry for that mistake, would give us cos 3t minus pi over 2 plus our last term, which would give us a half cos 5t minus 2 pi over 3. And if we look at this final resulting signal and we compare it to our signal right here, we can see that we have the two same values. So we just showed that they are equivalent whether they are in the exponential Fourier series form or in the traditional x of t expressed in terms of cosines. And this is our final solution for the problem number 2.